should decrease by a constant factor. I don't know, maybe.
No, it's definitely true.
I just solved it such that I set n minus n to the 1/3 equal to n over 2.
Yeah,
as
you
they
did
do.
what they did.
Yeah. And then I got.
Who's going first?
Oh,
You're
what is
Oh, yeah.
You should set this to something awful.
We can just all introduce ourselves. Do you want to
Yeah,
introduce yourselves?
Can I, like, does this have to be near my mouth? No, I think I'm good. Do you think I need this?
Yeah.
I think you need it.
Yeah, we definitely.
But, like, near my mouth.
Wait, are we recording it?
We are recording. It's recording. It's fine. I tested it. But we can't unplug this, otherwise I'll
Hi,
stop.
kids.
Okay, stop.
Okay.
Do I need this?
Yeah, this is yours.
I think you need a microphone.
We should
You don't
start
have to
so we
hold
can
it.
end.
Just put it. Oh, we can ask them.
We just.
Should I do an audio recording on my phone in case it's broken?
Oh man.
I think that I should.
You want to. This is just like the thing. Just put in your pocket. Wait, but we'll have to
Alright.
transfer.
If we're gonna introduce ourselves, you can take it off.
Oh, this is so much fun. Okay, I think we should start. Okay, here. Okay. Hi, everyone. We're going to go ahead and get started with the review session. This is our very first review session for midterm 1. Yay! My name is Arpita.
I'm Tiffany.
I'm Avni.
And I'm Varun.
Okay, let's get started.
Or should we say, like, we're gonna make a fiance spread? Or you can ask questions.
Did we
Alright.
make it?
We didn't make it yet.
Here, I'll make it. You can say that.
I'll be on Piazza. answering
Okay,
questions.
so-
What's space?
I'm making
Okay, so we're going to make a piazza thread for you guys to ask questions. We'll also be trying to come around and answer questions, but we know we won't be able to get to everyone. So we prefer you just ask on piazza, and then 2 of us will be monitoring that at any time and trying to get at that. We also wanted to just say that the main topics we're going to cover for this review session is like the first half of the content for midterm 1. So runtime, recurrence relation, divide and conquer, and FFT are going to be our main focuses for this review session.
You should stop at, like, 8:35. Approximately. Alright.
Do you need her?
You can press the button.
Okay, so we're going to start with some definitions about asymptotics.
You can sit.
And so basically, when we started this class, like our goal was to develop efficient algorithms, and the first step to doing that is to be able to figure out how fast something runs, and we use asymptotics to do that. And so we have sort of 3 different ways that we create bounds for algorithms. So we have our upper bound, which is big O, and so basically the way we define that is we say if there exists some C where after large enough n, our function f of n grows at a speed less or smaller than or equal to c times g of n, then we say that it is upper bounded by g of n, or it grows at most as fast as g. We can say that it is omega bounded by g of n if the opposite is true, or f grows at least as much as g. And if both of the prior are true, we can say that they grow at the same speed. So we can also use limits to reformulate the definition we just gave. If we have 2 functions, then we can set up a limit quotient between them and say that if the limit as n goes to infinity of f of n over g of n is 0, then f of n is upper bounded by g of n, and the converse is true if it goes to infinity. Note that limits imply bounds, but bounds do not imply limits. This basically means that if I have a limit that's undefined or a limit that's a constant, that does not imply, an undefined limit does not imply that a specific bound. And so note that this is just a one-way relationship. This is an if, but not an if and only if. So one way that we can deal with situations in which we have undefined limits is to use this rule that we learned about in calculus. So essentially, if we have two functions for which, as we go to infinity, both of the functions diverge to infinity, we need to apply this rule. And so in this case, we can take the derivative of both f of n and g of n and use that to figure out the relationship between the two functions. And so some key rules to remember when we're talking about asymptotics is that most multiplicative constants can be omitted. So we don't really care about the constant before a polynomial or exponential or whatever it might be. A polynomial that is to a higher power dominates one that is to a lower power, and any exponential dominates any polynomial. But keep in mind, this is only if the exponential's base is greater than 1. And then likewise, any polynomial dominates any log. And so these are some good rules to keep in mind when you're comparing functions. And so one way that we can kind of visualize or understand why this is true is by looking at how these functions look, or when you graph them, how they grow with time. So we can see that in this plot, when we're at small numbers, like all of the functions seem to intersect. But as we get to high values of n, it's pretty clear that the logarithmic function is lower than the square root 1, which is lower than the linear 1, n squared 1, which are all lower than the exponential 1. And so looking at this is often a good way to kind of justify these rules to you. Okay, so now we're going to do a practice question. Here you basically have to just apply the rules you've learned to sort the following functions in order of asymptotic complexity. So I'll give you maybe 2 to 3 minutes to do this, and then we'll go over it.
It wasn't there. I just posted this one. It didn't come up.
Yeah.
You got it. There's no question. Yeah. What is? Did anyone look at this? Okay. I can answer this. Probably.
It's basically just the first one's constant.
Yeah.
The next one is basically n to the 1.5. This one's basically n squared about the function.
Oh yeah. Yeah.
Can you also quickly tell them that we have a question thread?
Yeah, so our question thread on Piazza is now live, so feel free to ask questions there.
You're talking, but you're standing. Sorry.
Alright.
Okay, we're going to go over this question now. Okay, so we can basically apply the rules that we just talked about in solving this question. Some of the functions are just made to look a little deceiving, but it's the same rules that we saw before. So the first one looks like a really large number, but we can see that there's actually no n in it. So it is constant, so that's our lowest runtime. We see that the fourth one, n square root of n, is effectively n to the 1.5, which is smaller than n choose 2, which is on the order of n squared. So our second function is f4. Our third one is also polynomial, but one of a higher, with a higher exponent, so that's f3. And then the highest one is f2, because that's an exponential. Okay, so the next thing that we're going to talk about is master theorem. So when we're evaluating the asymptotic complexity of a function, sometimes it's somewhat difficult to figure out how quickly it runs. And so we write these things called recurrence relations to be able to take one step of running this algorithm and see how long it takes and use that to kind of derive the rest of the runtime recursively. And so master theorem is this theorem that allows us to, for recurrence relations of a certain form, it tells us what the runtime associated with them is. It's important to note that master theorem just comes from analyzing a recurrence tree and seeing whether the bottom layer or the top layer dominates, or whether all levels contribute equally. And so those are kind of our three cases. The first case refers to the situation in which the last term over here dominates, and the middle case refers to the situation in which all levels contribute equally, and then the bottom case refers to the situation in which the bottom level of a recurrence tree dominates, and so we have n to the log base b of a. And so we can kind of look at and apply these rules to solve recurrence relationships. In situations where our master's theorem may not apply, as you can see here, it may not apply because we don't have a d that we can use. We can draw out the recurrence tree and use the same idea as was used in deriving this theorem. And so I'll give you guys another few minutes to work on this, and then we'll go over that. so we're gonna go over this question now. So the first step to solving any sort of question where you cannot use Master's theorem is to draw out the recurrence tree. So if we draw out the tree, we see that at every level we split into nodes that have n over 2 log n over 2 runtime. And if we add up the amount of work done at all the nodes on a given level, we see that it is n log n over 2 to the I. And if we then look at how many of these levels we have and add up everything, we can create a summation to add everything up. In this case, the math may look complicated, but what ends up happening is that we can essentially ignore the n over 2 and n over 4, and we can upper bound them by n. And so we can say there is n log n work done at every level, and then there is log n levels. So in the end, we have a runtime of n log squared n. You might be wondering, how can I do this upper bounding and still get a theta bound? The reason we can do that has to do with the math we're doing there. Well, we figure out that the summation of all of the things that we're subtracting, 1 plus 2 up to log n, ends up being on the order of log squared n over 2, which is simply a constant factor that we can end up ignoring. And with that, we're going to move on to the next section.
Okay, so now we're going to be talking about divide and conquer and how that works. So the typical pattern is first we divide into smaller subproblems, and we solve those subproblems recursively, and then combine those results in what is called conquering, hence the divide and conquer. So the typical pattern that we can see if we represent it in terms of symbols is we have our original problem as t of n. We divide into smaller subproblems, which takes some amount of work we can represent as S1 of n. And then we solve the subproblems recursively by creating smaller subproblems, a t of n over b. And we combine the results in some other work, S2 of n. So if we do the analysis, we can sort of apply Master's theorem typically, not always the case, but typically you could then use this recurrence relation where you have t of n equals a times t of n over b plus theta of s1 of n plus s2 of n. So combining the work you've done per level plus this splitting up. Okay, also some examples of subproblems is you can have an array and you can split it up into the left and right halves, or trees where you can split them up into subtrees and then solve your problems on those subtrees. Okay, cool. So let's go ahead and do our first practice problem. It's called peak finding. Here, go ahead and read the question and spend a couple of minutes trying to solve it. And this over here is just an example of one run of peak finding. We'll be answering questions as well. So I'll give you guys around 2 to 3 minutes to work on this. Yeah.
Are we only returning the index of a single key element?
Yeah, find the index I, yeah. Yeah, because those are just possible returns. Yeah. try to work on this problem. So let's quickly just run through this example. Here we can see that the elements 8, 13, and 6 all qualify as a peak element because the elements to the left and right of them are both smaller than them. So we can return any one of these, the indices of any one of these elements. Okay, so the algorithm to solve this would require some divide and conquer, as the name implies. So what we would have is we would take the very middle element. So we can just find the middle element by taking the size and getting the middle element and comparing that element to its neighbors. So that's typically just going to be an O of 1 runtime operation, a constant time operation, because you're just comparing with the left and right elements. And if you see that this middle element is greater than both the left and right elements, then you go ahead and return that, and that's your solution. But in the case that it's not, then you have to consider the two halves of your array. So if the middle element is greater than or equal to its neighbors, if the element to the left is greater than that middle element, then you recurse and use the algorithm on the left half of your array. Likewise, if the element on the right is greater than the middle element, then you recurse and use the algorithm on the right side of the array. So hopefully this brings some intuition on how we could find the runtime, where we have, again, like the divide and conquer, where we have t of n split into t of n over 2. So notice in the master's theorem, a is just 1 here, because we're only using 1/2 of the subproblem, 1/2 of the problem in the future step. And then we're doing some constant amount of work, like I said, in the comparison when we do each step. And so we can see that at each step it keeps getting reduced by 2. So overall we would have log n steps. We'll answer your questions in a minute. And then, so yeah, or you can just apply the master's theorem, apply master theorem on this. Yeah.
So each time you prune away half of the array, so what can be the case if our only target is the part we prune out?
So that's why you have to make sure you prune the correct half out. It's not necessarily sorted though. So peak element doesn't really have to do with sorting. It just compares the elements that are next to it. Maybe we can address your questions and then when I give you time for the next problem, just so that we stay on track. Is that fine with you guys? Okay. Just remember your questions. We will come around. Okay, so let's go ahead to problem 2. I'll give you guys a couple of minutes to work on this, and if you guys have a question on the previous problem, we'll be coming around.
So much easier. Alright. Okay, now that's good. I'm going to explain the solution to this problem again, and I'm going to draw a picture, and I think that it'll become clear. Okay, so the idea is that by using only local information at your current point, you can tell whether there's going to be a peak on that side. So say you're at your current point, and you see, can you all kind of see this at least? Alright. Say that you see that if you go to the right, the number gets bigger. So there's only two possible cases for what happens in the rest of the array on the right side. The first is that it continues going up, and then at some point goes down, in which case there must be a peak on that side. The second case is that it continues going up forever until the end of the array, at which case we define the last element in the array to be a peak. So, as you can see, given that we only have the information that it goes up at this point, we know that on that side there is a peak. It doesn't matter what's happening on the left side of the array. Okay, I hope that makes it clear. Continue working on problem 2.
I think I didn't save this one.
Ah.
Yeah, the second one. Okay, okay. What are you doing?
Is this a different problem?
Yes. Oh, I don't want to explain. I don't want to do this.
I'm giving them away.
I forgot how to do this.
I'm giving them away. Oh, you could look at it.
Yeah, I have it also.
They're both on the maximum value. Oh, it's just A of 2. Is this correct?
Hmm? Yeah.
And they can repeat. Oh, they can't. I has to be less than.
I have this. So yeah, we have 2 cases. 3 cases where it's either both are in the
Both in the left,
left
both
half.
in the right, or one in the
Yeah.
Oh, this was like a homework question.
Really? Which one?
I can't remember. Like during our time.
Oh.
If n is less.
Yeah, I think we had this one.
What is n? Oh.
And it's a size.
If let k equal.
Just half. Right? So you split up the array and you find the max of each of the halves. And then you say, no, not max. You find the maximum, so you run this algorithm, I plus j squared on the two halves,
Okay.
and then you get the max of that, and you get the max of the right half, and then you get to compare the maxes to see
And compare the max to the situation which you have.
in one. Yeah,
Okay. Yeah, no, we don't really have to.
yeah. And then the runtime is just
Wait, when
2
do we
t n
do
over
that?
2 theta of n.
How do we do that? What is it?
But you do the left half, you do the second max, so you have the max on the right side, and then you try to find the second max on the left side. That doesn't make sense,
What
right?
does that mean?
Okay, so you find the maximum element in A, and then you only look at elements that are less than A, the indices to the left of it,
Yeah.
and then you compute A of the left
But you
element.
don't. It's not recursive, right? You basically just find the maximum element, and then you find the maximum element smaller than it.
Yeah. Well, yeah. And you also do the maximum element that's greater than it when you switch I and J. Like you kind of do,
What do you mean?
like A of m plus A of L squared, right? So J, like when you find the thing that's to the right. I don't know actually what the point of this is. So the point is you find the best.
Can't you basically just find the maximum? Oh no, you can't because what if it's the opposite?
Yeah. So
What is
you're
M? Oh, index of the maximum.
yeah, and then
So
you
you say
look on the left half, and you find one. So if you look on the left half, then you care about A of L plus. I don't know how to explain this.
no, it must be okay. It must either be that max element or something on the left half, or what's M?
M is the index, right? So
Or it's something on the right half.
yeah,
Oh, is it sorted?
no. The sorting doesn't matter. Yeah, it does. Why? No, it doesn't.
Oh, it's
Sorted
index.
the index, yeah.
No, but what about the situation in which it's best to take two things that are not max? Oh, that
That
never
won't.
happened.
Yeah, that wouldn't happen. Why wouldn't it happen? Because then.
Oh, the maximum would either be the left one or the right one.
Yeah.
There might be a situation in which
When could that happen?
no, it's
Negative?
I'll tell you, no, the situation is that if I have something where the left one is my maximum,
Yeah.
right? If I have a situation where I have a maximum but it's really to the left, okay, and all the good stuff is later on. no, like a bunch of other
That's
stuff
why
is
you're
later
doing the second step,
So
right?
then so in that situation, I have my maximum be the first thing,
Yeah.
and then I have something else be the second.
Yeah.
So that's
But if you have some negative thing, then it won't be the max, but it'll help with the square.
no, but it doesn't matter because it checks, it iterates through everything in check.
No, but I'm saying, suppose you have like negative 100. That'll never be your maximum element.
I thought they're non-negative.
Or are they?
Non-negative.
It says? Where?
It definitely would not work if it was negative.
Okay, yeah, no. Okay, I think we can discuss it now.
What would happen? How would you do if it's negative?
I don't know.
I guess you take absolute value.
Or
No, that
you
doesn't
would
work.
square it.
I don't have.
Yeah, you wouldn't do the absolute value because
Yeah.
then it doesn't necessarily work in the other case. Okay, guys, let's go ahead and discuss this problem. Hopefully you guys got ample time to come up with some solution. Okay, so this problem is asking us to find the indices such that a of I plus a of j squared is maximized. That value is the maximum value possible. So there are three possible cases for these indices I and j. Either we can have I and j in just the left half of my array, or I and j could be in the right half of the array, or I could be in my left half and j could be in my right half. So now I've kind of like come up with this divide and conquer strategy where I can divide my initial array into two halves and then solve the subproblems separately. So how I would go about doing that is basically finding, so x would be finding the maximum value of a of I plus a of j squared just on the left half. So finding that maximum value just on the left half. Y would be finding that maximum value just on the right half. And then I would have this other variable z that would take the left half, find the maximum on the left half, and then take the right half and find the maximum on that right half and square it. And that would be my value if I considered both halves at the same time. And then I would find the maximum across those three numbers. Does that make sense? So it's a divide and conquer strategy. Okay, so for the runtime of this problem, as we can see, we're doing a split on two halves. So we have, and we care about both halves. So we have 2 times t of n over 2, right? And the work that we're doing is theta of n per level. So if we just use mastery theorem on this, we would see that the runtime is theta of n log n. Okay, yes. Or-
If we just start at the top two indices, wouldn't that have the same runtime?
Yeah, that would just require sorting the array. So this array is not necessarily sorted. Okay, so there's also an optimization to this problem where we don't necessarily have to use divide and conquer. So divide and conquer is a great strategy, but sometimes doesn't result in the best runtime, right? So let's look at something where we have slightly better runtime, where it's just linear. So here what we're doing is, so one thing to note in the problem statement is that we're dealing with non-negative numbers. Okay, so this only works when the numbers are non-negative. And what we do is we find the maximum element in our array, and then we look at two cases. Either that maximum element can be our left number at I, or it could be our right number at index j. And what we do is we consider all elements that are to the left of m and check if that value of a of l plus a of m squared is greater than our best max currently, or we look at all the elements to the right of m and then consider the sum where a of m plus a of l squared is greater than the best max, and we go ahead and return that best max value. So this would be a linear time algorithm because we're just finding the max element and then looking at each element only one time when we're doing our computations. Can we answer your question while we walk around? Okay. Yeah. Okay, so that's all we're going to do for divide and conquer. And then, yes. So, and if you have any questions, we'll be walking around, but we'll be going to the next segment now.
We have so much time.
Should I do one more problem?
I guess we can just do it after.
Yeah. I think this is not loaded. I hit it here.
Are people asking questions on Piazza? Okay, so if we have time left over at the end, we could do more divide and conquer problems, or we can do more FFT problems, or whatever you guys want. But we're going to start talking about FFT now. FFT is often a point of confusion for students in this class. There are a lot of moving parts, and there are a lot of things to keep track of, so hopefully this overview will be helpful to you. Okay, so the first thing about FFT is that it uses complex numbers. Specifically, the complex numbers that it cares about are the nth roots of unity. So the nth roots of unity are the solutions to the equation x to the n equals 1. So the values of x for which this is true. And omega n, which we call the principal root, which is e to the 2 pi I over n, is always a solution to x to the n equals 1. If you take it to the power of n, you'll see that it indeed equals 1. So we care about the principal root because all of the other nth roots of unity are all powers of the principal root. So if we look graphically at the complex plane, the nth roots of unity divide the unit circle into n equal slices around the circle. So in the picture, we have the 8th roots of unity, where if we take the pizza of the unit circle and we divide it into 8 equal slices, that's exactly where the 8th roots of unity lie on the complex plane. So omega 8, which is the principal 8th root of unity, is at pi over 4, and all of the other ones are multiples of that angle around the unit circle. Okay, so familiarity with complex numbers is useful for understanding FFT. Hopefully you understood what I just said. But the important fact for FFT and why we're using the nth roots of unity is that if you square the two nth roots of unity, what you get back is the nth roots of unity. So we'll see that this is important for why FFT is a divide and conquer algorithm. Okay, so before we go to there, I'm going to talk a bit about polynomials because we're using FFT to multiply polynomials. So the normal representation of a polynomial is called the coefficient representation, where you list out all the coefficients of the polynomial. In the coefficient representation, if we use our normal multiplication algorithm, which you might have learned in high school as FOIL, where you multiply every term by every other term, multiplication takes n squared time because you have to do n squared pairwise multiplications. But we want to be able to multiply polynomials faster than that. So we take advantage of an equivalent representation of polynomials called the value representation. So as you probably learned in CS70, a way to uniquely identify a polynomial of degree n is to evaluate it at n plus 1 points. So this is useful because if you want to multiply two polynomials that are already in the value representation, all you need to do is pointwise multiply their arrays. And you can see how this only takes linear time. So we want to be able to multiply polynomials quickly, but we are given polynomials in coefficient representation. So the purpose of FFT is to convert from the coefficient representation to the value representation, where we can do a really fast multiplication, and then we can go back and we will have done in total less than n squared work. So to explain that more, I have this picture. We're going to go in a roundabout way around the circle in order to multiply in a way that's faster than n squared. So FFT is n log n time. We start with the coefficient representation, we go to the value representation, and then we perform a linear time multiplication there, and then we can go back in n log n time as well. So in total, it's only n log n time, which is better than n squared time. So roundabout circle, better time asymptotically. Okay. Next, I'm going to talk about the inputs and outputs of the FFT function because it's easy to get confused about what actually FFT is for. So I just said that the purpose of FFT is to get to the value representation of polynomials, right? So there's two inputs to FFT. The first is the coefficient form of the polynomial. The second is a number n. And that number has to be a power of 2 that's bigger than the degree of p in order for our algorithm to work. Okay, in this example, we are using n equals 4. So the output of FFT evaluates p of x at the nth roots of unity. So in this case, we have the 4th roots of unity, 1i minus 1 and minus i. And what is returned to you by FFT is if you plugged in each of those roots of unity into p, these are the numbers for the value of the polynomial at those points. Okay, let's go. All right, let's talk a bit about the mechanics of the FFT algorithm. So you start with a polynomial of degree n, and the idea is that you split it into two polynomials. You take the coefficients on the even degree terms and the coefficients on the odd degree terms, and you make two polynomials that are each of degree only n over 2. And then you can use this formula, p of x equals e of x squared plus xo of x squared, and you can combine the results together. So if you plug in x squared into e of x and o of x and you add them together, you'll see that it exactly equals p of x. It's a useful exercise to convince yourself of that. But this is a divide and conquer algorithm. We've split a problem of size n into two problems of size n over 2. Very good, that's the divide step. Now to conquer, we combine them together, and the key fact is that you can use the pre-computed results that you recursively computed on the n over 2th roots, and we know that if we square the nth roots, we get n over 2th roots. So that's the important property of the roots of unity for why FFT is possible. So this is the main idea of the algorithm: divide, conquer. Very good. All right. So now that we've peered into the box that is FFT, let's talk about how to use it as a black box to solve algorithm problems. So I think that the most important idea for how to apply FFT is the formula that's on this slide. So if f is a polynomial with coefficients a, and g is a polynomial with coefficients b, and we want to multiply them into a polynomial with coefficients c, and we want to look at what the coefficients of the product are, the way to think about it is that the terms that contribute to the degree k coefficients in the product are the terms in the original polynomial whose degrees add up to k. For example, the x squared term comes from x to the 0 times x to the 2, and then x to the 1 times x to the 1, and x to the 2 times x to the 0. So if we look at the formula, we have ai and b k minus I, and we see that I plus k minus I is k. So we look at all of the pairs of terms whose degrees add up to k, and we add them all together. Okay, so if you're not convinced that this formula is true, I think that if you understand it, you'll be able to do a lot of problems. Okay? Okay. All right. Another thing that you guys talked about in lecture was successive dot products, which is a related problem. So the inputs are two vectors, x and y, where y is potentially a smaller vector than x, and then it returns this array of successive dot products. So let's look at some pictures. So here are two arrays, x is 1, 2, 3, 4, y is 5, 6. And the idea is that you line up y with x at all of the different possible locations, and then you compute the dot product. So first you line up y with the first two things in x, and then you compute the dot product, and that's the first element in your output. And then you shift y over, and you do the exact same thing again. And lastly, you line it up with the end of x, and you compute the dot product again. So the output is this series of dot products when you shift y and then you move it over and match it up to different parts of x. So that's the problem statement. Why are we talking about this? Successive dot products is a problem that can be solved using FFT. So without too much manipulation of the inputs, we can use FFT to solve this problem, and it takes n log n time. So if this can be solved with FFT, where are we talking about it? It's like a higher level of abstraction than FFT, where if you see in your problem that you need to compute these shifted dot products, then you no longer need to explicitly write out the polynomials or refer to polynomial multiplication in order to solve the problem. So for example, the viruses problem in homework 3 was exactly matching up these strings of ones and negative ones and computing the dot product. So you can see how this is a pretty general problem statement and is quite useful as a black box. And when you use it as a black box, all you need to do is specify the vectors x and y. And then you don't need to write any polynomials, and everything is great. Okay, successive dot products is also called cross correlation, which you may have heard about in E16A or something like that. Okay, let's do a problem. And if you have any questions about FFT, people will be around to answer them. first, there's a typo in one of these slides that I said was important. This I equals 1 should be I equals 0. The sum starts at 0. I'll fix it. Okay. Let's talk about this problem about water buckets. So the idea is that you encode each of the sets A and B in polynomials. You encode the bucket sizes into degrees, and then you multiply them. So that when you multiply them, all of the terms, the degree will be pairwise, all pairwise sums of the buckets in A and the buckets in B. So that means that if we take the coefficient on the degree I term in the product, that will be exactly the number of ways that you can add one number from A and one number from B and get I, which is exactly what you want. Okay, the slides are posted. I'm going to show the next problem. Raise your hand if you want more time for this problem. All right, 1 more minute. So the way to do this problem is you will have to think about what it means for a number to be represented in binary. So if you look at a number 1011 in binary, what it means is 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. Like that's what it means to be in phase 2. And if we look carefully at this, we can see that it's a polynomial evaluated at x equals 2, where the coefficients are the zeros and 1 digits. So the way to multiply two numbers a and b is that we take their polynomial representations, by which I mean you take their digits as the coefficients of the polynomials, and then you multiply them together, and then you evaluate that polynomial at 2, and that will exactly be the multiplication of the two binary numbers. Alright, one more FFT problem. Pretend you have as many of each coin as you want. So the k coins that you sum up don't have to be unique. Okay, let's do this question. Alright, so we have a bunch of coins, we encode them in the degree of the polynomial, and then we take that polynomial and we take it to the power of k. So then if the coefficient of the degree d term is non-zero, then it was possible to take the coins and add it up to exactly d. Take k coins and add it up to exactly d. This question is very similar to one of your homework problems, which is called triple sum. This is like k sum. But, alright. Okay. Arpita, let's do more divide and conquer questions. Okay, if anyone has any questions about anything that was covered in the review session, we'll be walking around and also you can get outside. But we're going to do more divide and conquer.
Okay.
Voice recording.
Yeah, we'll be walking around, so you guys don't have to keep your hands raised. Who's ready for some more divide and conquer? Okay. Okay, so let's go ahead and work on problem 3 from the divide and conquer set. This is an interesting problem, so why don't you guys take some time to work on that, and we'll be coming around to answer some questions.
condition for an That's so I'm hung up on this like one this talking about the dominance. Obviously, there's like this one. Okay. So if there's anything in this, it's almost yeah. So this one is dominating this one. Then it's like what if there's something here, either of these. Oh, sorry. So like what I was thinking is that it's like so if there exists oh that's right. I like this. Yeah, which is a little idea because I was like, yeah. That's smart. Similar to counting the idea is like we want to learn, we know nothing. Maybe it's easier to find things that are known. There's a stricter condition that goes on. Really just the anything this one right, I think oh, yeah, that'd be our next step. Once you get to it, here we turn up this little head here. Well, look, the idea that after, like, it's not like
Okay, I got a little bit delayed in coming back here, but hopefully you guys got a lot of time to work on this. So this is an interesting question that uses divide and conquer, and let's just go ahead and jump into the solution. So here, first, just some intuition and high-level approach. We have 4 different cases, so we need to consider both the x and y coordinates, right? And we only say a point x2, y2, so dominates x1, y1, if both the x coordinate and the y coordinate are greater than the coordinates for x1 and y1. So as you guys can see here, x2 is greater than x1 and y2 is greater than y1. So we can say this point x2, y2 dominates the point at x1, y1. Whereas in the other cases, either y1 is smaller, either y2 is smaller or x2 is smaller when you compare the coordinates. So hopefully you guys got something like 4 cases here where you could check each of those cases and see where it's dominated and where it's not. Okay, so let's go into the algorithm. So here, okay, so we want to find an O of n squared algorithm for finding the undominated points. So those points are not dominated by any other point in our set of points S. So how many of you guys actually worked on this and have some ideas? Because I know I didn't show this slide up. Do you guys want a minute to work, just like to think about it some more? No? Okay. Okay, let's just go ahead and discuss it then. So, since it's an n squared solution, you should intuitively think that you're going to look through so you're going to go through each point, and for each point, look at all the other points. So kind of like a nested loop as we have here. So you check for each point I, then for each point I, you check for every other point that's not equal to I, check if that point dominates I. If it does, great. If it doesn't, then it's an undominated point. And yeah, and this algorithm, again, will take O of n squared time because of this nested loop structure. Okay, so I'm going to give you guys a couple of minutes to work on part B. So here we're, go ahead and read the question and see if any point in S2 can be dominated by a point in S1. I'll give you slightly less time this time.
Last question.
Yeah. Hopefully.
This was on my midterm. I got it wrong.
I probably would have gotten it wrong too. It's okay. Let mx let mx be the median value of the x values.
Okay, so let's go ahead and discuss this problem. I know it's a little bit less time, but yeah. So here we're saying let mx be the median value of the x values and have a set of points that have the x value be greater than that median x value. And then similarly, we'll have points that have x value less than the median x value. So we're saying, can any point in S2 be dominated by any point in S1? And the intuitive answer to that should be, what? What do you guys think? It should be, sorry. It should be, any point in S2 can dominate any point in S1? Raise your hand. Nobody? Okay, any point in S2 cannot be dominated by any point in S1? Yeah, okay, so that's true because for any point x2, y2 in S2, and any point S1, any point x1, y1 in S1, x2 is greater than x1. So x2, since it's greater, that point can be dominated by something that's smaller. Okay, so let's look at part C. I'm going to discuss the answer for this. So here it says briefly describe an O of n log n time algorithm for finding the set of undominated points and briefly justify why the algorithm is correct. So hopefully the previous two parts helped you build some intuition as to what we'll do here. So n log n runtime should make you think of some divide and conquer where we're dividing it into two halves. Okay, and doing some sort of linear work. Okay, so here, as we can see, the divide part would be taking my initial set S and dividing it into the two halves, S1 and S2, and finding all the undominated parts in each of those two halves. So the way I would divide it is by using that median x value and taking S1 to be all the points that are like in the left of the median, and S2 to be all the points to the right of that median. And then I'd run the find undominated algorithm on each of the two halves. And so the conquer part would be where I have all the points that are undominated in S1 and all the points that are not dominated in S2. So since they are not dominated by either set, they are just undominated points for the total set S. And so those are the points just in the undominated set of S2, right? And then we can find all the points in U1 that are not dominated by the points in S2 by considering the Y values, okay? Because we'd have to consider the Y values because here we've considered only the X by considering the median along the X-axis. So next we'll consider the Y-axis and see all the points where the Y value of the points in S1 is greater than the Y value of the points in S2. And the way we could simplify that down is just saying Y1 is greater than the maximum Y value in S2. And that will form our undominated set from U1. Okay, so so kind of like what I hinted at before, this will be a divide and conquer where we're splitting into the two halves. So we have 2t of n over 2 and O of n work per level. So the total runtime would be O of n log n. Yes, 1 second. Okay, so I think this will be our last question, and then you guys can come up and ask us questions if you have any. But the review session is, I think, officially over. We have 15 minutes. Okay, you had a question. We should stop the screen recording.
If you find undominated point U2 over here,
Yeah,
its x value is going to be more than all of these x values.
exactly.
So
That's why it's not dominated by anything in S2. Yeah.
So, I was looking at the slide.
Yeah.
Okay. So, I understand this all and why this, like, these are also undominated points. But this is kind of like a black box recursion type thing,
Yeah.
where you're like, okay, we can just find the undominated ones.
Do you have any
And
questions?
I understand, like, abstracting
So,
with,
like,
the
you're
black
saying,
box,
like,
except
after
you still
splitting
have to have some
down,
sort
like,
of base
the
case to
value,
find.
That's where
you're
so
following
what
the
last time is coming
probably
from, right?
closer
Like
to the
finding that median.
stuff. Okay.
So ultimately, the last step, you'll sort of just have that,
Okay.
like, pair, the three elements, I guess, because you have the median, you have the left and right halves. Actually, you would just have one element.
So
Your
what
base
we're
case.
doing is we're breaking it up.
Wait,
Wait, how
into
does it get to the
left
base
and
case
right
again?
Yeah.
That's what I'm confused.
Yeah. So here we.
Yeah.
So if you find any point, if you
So basically, the
recursively
recursion
call
looks
this
like
one
you take all the points
Uh-huh.
and you like
find
slice,
some
and then you
undominated
like
point,
Yeah.
find undominated between
X
this
value
and
is
like
still bigger than all
this,
the
like
previous
points
X
that are like
values,
at the
right?
top of this, so it looks like this.
XY is greater than all the previous.
And then you like, I guess. So it's kind
So
of like you. It's like you
undominated-
chop off like if this is the highest one.
Yeah.
If you go back here.
Yeah.
If this is the highest one, it's like you chop off everything in here that's not above that.
Yeah.
So it's like you then recurse on like some sort of like L-shaped
So-
pizza slice like this.
Yeah.
And then you call the same algorithm on that again, where the median shifts over here.
Yeah.
And then you have
So
another
also-
pizza slice.
Yeah,
So-
and you know that this right half automatically will be never dominated by anything in this one, right?
Right, but it's still there could be domination
Stuff inside
within
of
it.
it. Yeah.
So then, if the base case recursion gets to this point where it's like you've sliced, first you slice off this, then you slice off this, then you slice off like some bigger
So
thing. So then, what is the
not
this look
exactly.
like?
So you're still finding the undominated within your
Right.
position 40.
Right.
So the base case will come like on both halves. Because, like you said, yeah, there can still be some undominated, some things that are dominated here. Like all these, right, are dominated by this one.
Okay, so it's like you take this and you cut it, and
Cut
then you
both.
look like a pizza. It's like a pizza on this and this. It's like it's or whatever. So like pizza happens in each half, and then in each half again.
Yeah, like, I think first we're just saying, yeah, sort of. I don't know if I was reading yeah, I think that's, so, okay, yeah, I would just say find the median along the x value, and then you would see, so that's how you're splitting it along the two halves. And then in order to find, so, and then splitting, right, and then you would also one value, and compare that y value. Then you would end up comparing y values.
When you have like
Yeah, yeah. If
or I
they're-
guess you could sort of just do it down to some point that you like label to be constant, right? So
Yeah,
it's like you can even almost abstract it to that, which is just like you just declare at one level, just like you just do something.
Exactly. And like that's where this step comes in because you like here I've just shown you the case in this like high level picture where I'm condensing what I get from the left side and the right side, right? By using the y values, but you have to kind of like imagine that on a smaller scale. So maybe work through an
I think
example.
I can see how this works now.
Yeah.
Is this seems like a really hard problem. Is this like the level of difficulty of the example?
Like I think this is like something like this would be fair game.
Okay. Thank you
But
so
I think
much.
yeah.
Thank you.
Yeah, no problem. Yes.
X is always
No, it's okay.
I think I found like at least my idea of which situation I wanted to
The
check.
coefficient.
Yeah. Okay. So for coefficients, I felt like it's a scenario where you want to find all the combinations that add up to k,
Yeah.
because A0, like where each
Yes, right? Because no, actually, no add up. They multiply. They have to multiply.
or like these coefficients, like
So in her slide, yeah.
like
so,
these values,
Yeah.
like 0 plus n minus 1 is equal to k. Then 1 plus n minus 2
Yeah.
is equal to k.
Yeah. So these are not really like these are kind of like the indices of the coefficient. It's not really the
Yeah.
coefficient itself. Does that make sense?
It does, yeah.
Okay.
So like these indices will add up to k.
Yes.
But in the exponent situation, you want to find all values that can be expressed as a sum of k terms. Like for example, for the
Not exactly again.
I
I think unless I'm misunderstanding.
I could be just like this is like in this situation k would be 3.
IJ or
'Cause you're trying to
like your
maximize
K
N.
is different from that K.
Sorry, k. By what I mean by k is like a constant value.
Okay.
So like in this situation, the constant is that these subscripts all add up to some constant.
Okay.
But in the like in this situation,
Oh, I guess so, right? So in this, but there you'll be considering the product polynomial.
yeah,
Right,
like the
then-
constant here would be the fact that like
Actually, no, you wouldn't care about the coefficient again.
you wouldn't care about the coefficient
No.
when p of x, like taking here, k is equal to 3, so p of x
Oh.
to the k. So
Yeah,
like,
yeah.
I guess what I was trying to figure out is like when you're given one of these problems,
Yeah.
you're given some constant value, like either like add up to this number
Yeah.
or like all combinations that. Like I
okay,
guess I'm trying to
not
figure out how like
really-
looking at a problem you can show.
Okay, maybe, okay, I think what I was trying to get at earlier was like, the reason here, it's not because I'm given some constant value n.
Oh, I don't mean the constant value n. I mean the constant value that there are 3 numbers that you're adding up to n.
But
then
that
you're-
doesn't necessarily indicate that I'm using FFT, right?
You